Okay, good. We're like, I brought it.
Okay, let's see what we got here. You guys, we have a lot of thoughts about this. Where are we here? We're answering it. Everybody just get an answer here. The majority of the points are participation. We will start class every day with a few sort of quiz questions, and even those, I think, are 60% is participation. But anything we ask kind of along the way is all just, I want to know what you're thinking. So I'll say that. Everyone will now change their answer to what they think the right answer is, but nonetheless, we'll go on. So gaseous water here is what we mostly think. Is there someone who can tell me why they think the gas is higher in enthalpy? Yes? Okay, so you're saying that to be a gas, I have to be at a higher temperature. And that's absolutely true, that if I get the temperature really, really high, most things end up as a gas. But what if I'm at the boiling point? I'm right at the boiling point. I got liquid, and I got gas. Same temperature. Oh. Are they the same then? Does it depend on the temperature? If you think about the enthalpy, what are you thinking about for the substance? It's a very hard ranging question to ask. Yeah? More microstates. You're thinking entropy. I'm thinking enthalpy. We'll get to entropy in just a second. I like thinking about entropy. Yeah, the enthalpy. The heat. Okay, so everybody is probably thinking about the heat. And we just beat it into you over and over and over again. Enthalpy is heat, enthalpy is heat, enthalpy is heat. That's how we measure the change in enthalpy, is it's related to heat. But when you think about the enthalpy of something, you should think about its energy, and it's, in particular, its potential energy. Okay, so I want you guys to wrap your heads around that. Enthalpy, we're thinking about potential energy. And gases have a higher potential energy than liquids. Why is that? Intermolecular forces. So it's definitely true gases is the answer. But we don't know why. Gases have a higher potential energy. Why? The molecules aren't next to each other. They used to be right next to each other. What does it mean to be attracted to something in a molecular sense? It means that when you're next to the molecule, you have a lower energy. So if you have to pull the molecule apart, you have to put energy in to overcome those forces. And so we go from a low energy state, everybody's next to each other, to a high energy state where everybody's far apart. And so the enthalpy is higher in the gas. And in fact, if I want to do that, if I want to go from the liquid to the gas, I'm going to have to put energy in. So even if I'm at the boiling point, the water is 100 degrees, it's on the stove, it's boiling. If you want it to actually convert from liquid to vapor, you have to keep putting energy in because the gas is the higher energy state. Okay, so thinking about that, we want to think about the sign of vaporization. So now, delta H vaporization, I want you to think about what that is. This is define, remember what vaporization is, how we're going to define final states and initial states, and how we're going to think about the sign of vaporization. So this one you should be able to do very quickly because otherwise we're not going to get to what I want to think about today. Although this is well along the way. Just one. What's the sign? Positive, negative, zero. Okay, well, I'm going to leave it open here while I show the answer. Oops, hide the answer. I want to see the report. There we go. Positive. Okay, most people think it's positive. All right, is it absolutely correct? Why? We need to think about the final state. This is a liquid goes to a gas. Final, initial, and so delta H of vaporization is the enthalpy of the gas minus the enthalpy of the liquid. And if the gas is higher than the liquid, when you subtract the two, you get a positive number. That is, the gas is higher in energy. So what does that look like? Again, liquid, molecules all next to each other. They have low energy. Low energy is stable down at the bottom of the hill. Why? They're next to each other so they can experience those intermolecular forces. Far apart, no intermolecular forces. It's not that the forces don't exist, it's that you're too far away to notice them. Okay, intermolecular forces are very distance dependent. Okay, all attractive forces have some distance dependence to them, right? If I am taking, this is a bad example, we have to think about things that we can touch and feel. You guys can touch and feel magnets. Magnets are not the same thing as the intermolecular forces, but it's attraction. And when you get the magnet a certain distance away from the refrigerator, you don't feel the pull anymore. Why? You're too far away. It's not that the magnet has changed, it's you're just far away from the refrigerator now. And then you get close and then all of a sudden, wham, it sticks. The molecules do the same thing. When they get close, they all of a sudden stick together, but you pull them apart, all of a sudden they don't notice each other anymore. They just move around in the gas phase. So once you pull them apart, overcome those pain, or it's going to vary with the temperature. Okay, we have a little technical difficulties here while we're in this question. Okay, while we're working on this, let's see what we've got here. Okay, isopropanol, most of us go with. We have a handful going for acetone. Is there somebody who can tell me why they think it's isopropanol? Quickly, yeah, right there. Why does it require more energy to vaporize? Because it has stronger intermolecular forces. It has hydrogen bonding where acetone does not. Okay? More intermolecular forces, that's going to be bigger delta H. So here's the thing I want you to keep in mind for now for the rest of the semester, because this is a very important concept. Intermolecular forces, enthalpy. Intermolecular forces, enthalpy. That's what we're going to think about all the time. We're going to think about it for molecules. We're going to think about it for substance dissolving in water. How do we think about delta H? Intermolecular forces. Okay, so since intermolecular forces are going to be our enthalpy chunk, now we want to think about entropy. And so very quickly, we have another question, which is, which do you think would have a higher entropy? Let me just give my overview here. Higher entropy, liquids or gases. And again, the example is water, because that's the substance that we all know. But it's true in general. That is, liquid something, gaseous something, or they're exactly the same, or depend on the temperature. Okay, so let's look at this again. We're going to think about some very basic things to remember about entropy. So which is higher? Liquid, gas, they're the same, depends on the temperature. Most of us think it's the gas. Excellent. I like that idea. Can somebody tell me why they think it's the gas? Yes, right here in the center. Let's be quiet so we can hear what the answer is. Higher number of microstates for the gas. Yeah. In a liquid, where are the molecules? They're all right next to each other. You can rearrange them, but there's not very many choices. The gas has all of this space to explore. If you think about the same amount of molecules in a liquid, very small little area or spread out everywhere. Little tiny drop of isopropanol was on the plate. Now isopropanol is all over the roof. It evaporated eventually. Same thing with our acetone. So more microstates. So thinking about qualitatively in terms of entropy, how does it vary? Just try to remember. Make the volume larger, you get more entropy. Make the temperature higher, you get more entropy. Changing phases, I jumped ahead. Solids, low, everybody's beautifully arranged. Liquids, a little bit higher, not much, but a little bit higher. And then gases, much higher. All of a sudden you go from everybody being in their own little place to spread out all over the universe. And the other one is with reactions. More molecules, higher entropy. So if I go from lots of bonding and not very many molecules, big explosion, lots of molecules, that reaction is likely increasing the entropy. And most importantly, we're going to tie this up in terms of free energy. That's the thing we're always going to think about. But remember, it is the entropy of the universe that's always increasing. Second law of thermodynamics, the entropy of the universe always increases. Why? It's just the most likely thing to happen. Entropy is not some mystical force. More microstates just means better chance if something random happened that that's what's going to happen. And so everything in the universe is moving towards this most probable configuration. So with that, let's think about entropy for these two molecules, and in particular, delta S of vaporization. So first, you probably want to think about delta S vaporization in general. What's the sign? Is the entropy going up? Is it going down? And then for these two, which do you think is higher? Is the entropy change going to be large for isopropanol compared to acetone, or about?
Isopropanol? They have the same rate of microstates space.
Oh, I think changing the temperature.
If possible. Sometimes, no matter what temperature you make it,
Okay, let's see what we think here. Okay, we're totally nailed it. It's either the isopropanol or it's the acetone, or they're about the same, and we haven't fallen for the variable temperature. Oh, you guys can't see the results, so but now everybody's changed their mind because the first words out of my mouth were isopropanol. But before, they were all, oh no, there it is. Everybody was all about the same. the question is how in the world to think about this one. The intermolecular forces are the enthalpy. I said that like 4 times. I'm going to say it again. Intermolecular forces, how many ways can I arrange the molecules in the liquid compared to how many ways can I arrange the molecule in the gas phase? And there are certainly more microstates in the gas phase compared to the liquid. It's a big change. And the question is, what's the change like for each of these liquids? So gases always have a higher entropy in liquids. It's because of this big phase change. The molecules all next to each other to the molecules spread out and far apart. Almost every substance on the planet, the difference in entropy between the liquid and the gas is the same. It's the same because the molecules don't change. The molecules just change position. They used to be next to each other, and now they're far apart. And that's the big difference. And so as it turns out, delta H, or delta S of vaporization, is the same for almost every liquid. It's this random number, 85. 85 joules per Kelvin per mole. Just by chance, that's what it works out to. And it's because the molecules aren't changing. The molecules are changing position, but the molecules themselves don't change. So if this molecule has more entropy than this molecule, maybe there's a difference between them, but when I take them both up into the gas phase, the difference between those two is the same. So the change upon vaporization is nearly identical. There is one exception, one big exception. Big exception is water. If you don't learn anything in the world about liquids, you should know water is weird. Water is always the exception. Water is the exception because it has unbelievably strong hydrogen bonds. And it has nothing to do with the fact that they're held together more tightly. Does anybody know why it might be weird for water? It's not that they're stuck so tightly together. Anybody know anything about water, liquid water, that might make the entropy strange? Yeah?
It expands when it freezes.
Oh, it definitely expands when it freezes. It's totally bizarre, which is the same reason that it's different with the entropy. Yeah? It's more dense with its liquids, the same problem, same thing. Is that it has a structure. Most liquids, willy-nilly, the molecules are just oriented whichever way, and they kind of try to arrange their dipoles and this, that, and the other thing. Water is hydrogen bonded in this big network. You can just keep drawing H's to O's to H's to O's to H's to O's to H's to O's. And it is that hydrogen bond network that means there are fewer microstates than you would think for water when it's a liquid. Every molecule just isn't any old place. They're in particular places, all stuck together. And it's that structure of water that gives it these weird density properties, and it's the structure of water that means delta S is really big for water. Delta S of vaporization is really big for water. Everything else, it goes from kind of random liquid to random gas. Water goes from structure to...
Because gases have a higher entropy.
I don't know.
Yeah. So I think it's gases. Yeah. But then it goes to that it depends on the temperature.
Yeah.
This is just for water. Right? Yeah. I'm going to say yes.
Why?
This part shouldn't matter. Given is for approximately
That's your thinking? Okay. But here you're not comparing two different liquids. You're comparing water to itself.
Oh,
So you're comparing gaseous water to liquid water. You guys got an answer? No? Yes.
An extreme
Okay, let's have a look at what our answers are here. See where we are. What did we do? Let's see. Hello. Get something. Press the button. Okay, it's either liquid, or it's the gas, or it depends on the temperature. We did not go for it's exactly the same. As we're desperately all changing to it depends on the temperature, does somebody want to tell me why they think it depends on the temperature? Yes. Okay, so he's in a seminar one time, sitting over there, fancy speaker, coming from out of town, talking about what they were doing. Somebody asked him a question about why this happened. They said, well, it's because the things are moving towards their lowest free energy. And it's like, that's why everything happens. That's not an explanation, right? If anybody asks you why something's happening, you just say, oh, it's going to low free energy. So, low free energy, that is the stable place. So now the question is, which is more stable, liquid water or gaseous water? It depends. Why does it depend? Yeah. It depends on the temperature. Crank the temperature up to 400 degrees Kelvin, I can tell you, liquid water, not particularly stable. It will all be gaseous. And in fact, if we wanted to go to negative 85 degrees, liquid water, not particularly stable. Things do not go uphill in energy. So the positive delta H is not helping delta G be negative. Delta S is positive. That's what we want. Everything in the world wants to be positive increase in entropy. And so we've got these two things. This one is going up. That's going to give us a little frowny face. This one is going up. That's going to give us a little smiley face. That is, one of them is making the free energy go up. One of them is making the free energy go down. We have to say which one's going to win. It depends on the temperature. The temperature is 0. Everything is delta H. Temperature is infinity. Everything is delta S. In between, depends on where we settle. So we're going to try to find a very important point. We're going to try to find an important point where there's no change. Neither is more stable. Delta G is equal to 0. That's the point that we're interested in. We're going to spend the whole crazy semester talking about where delta G is equal to 0. That's the equilibrium point. And it's not that it's so super important. It's just that that's the place where things stop changing. Because when delta G is equal to 0, neither the products nor the reactants, neither the final state nor the initial state is more stable. Everything is the same. And when that's true, since delta H is equal to, or delta G is delta H minus T delta S, if that's equal to 0, I rearrange that, and what do I find? Delta H is equal to T delta S. So when delta G is equal to 0, I have this magic point. If I know delta H and I know delta S, I know the temperature at which that is true. So, what are we going to think about for a phase change? Phase change is that point, this dynamic equilibrium point, where it's not that things have stopped. If you're at a phase transition temperature, you've got boiling water, 100 degrees C, liquid water, water vapor. Are they identical? Or does it vary depending upon whether it's a liter or just a drop of liquid?
Let's just say delta S is 1. Delta H is 5.
say something without the data. If you had the data, it would be trivial. If I gave you delta H and delta S for both of these compounds, there'd be no problem to be able to answer without any problem. Without the data, follow. And what about delta S? There you go. So if I think about the two, I'm going to think about the temperature for acetone is delta H for the acetone divided by delta S for the acetone. This is the vaporization. And I'm going to think about isopropanol. It's the enthalpy of vaporization for isopropanol divided by the entropy. And as it's pointed out, delta H for isopropanol is larger. Delta S is the same. So larger delta H means a higher boiling point. This is the reason we can chalk up all kinds of stuff to intermolecular forces. Okay? If it wasn't true, it would be a disaster. We'd say things like stronger intermolecular forces, that should be less evaporation. Well, it depends on the entropy. But as it turns out, it doesn't depend on the entropy, because the entropy is the same. The entropy change is the same for all these substances. And so we can throw everything in terms of the vaporization behavior into delta H. Okay? It's not as easy when we get to melting. Melting, delta S of melting is not the same for every substance on the planet. And so unfortunately for melting, intermolecular forces is not everything. And so it makes it very hard to predict melting points. Melting points are really hard to predict. Boiling points, really easy to predict. It's all intermolecular forces. Melting points, it depends, because it depends on delta H and it depends on delta S. Okay? We want to think about now, how are we going to use this moving forward? We're going to think about phase transitions. Solids to liquids, liquids to gases, solids to gases. We're going to think about what temperatures do those things happen? How do we get a phase diagram to figure out when a substance is stable and when it's not? We're going to think about making solutions. Always, 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 delta H is going to be our intermolecular forces. The entropy is going to be the part that we're going to have to apprehend. Just to make sure you know, every day, when we come up here, I'm hand map some photos of your notes every day, put them up on the website to make sure that we have a good copy of student notes. And if you have a star or a candy wrapper and you want to make sure you get put down to the bonus points, you want to come up and find, I don't know if it's Lee or Connie's going to do it. Connie's going to do it. She'll be down there up front in a second. Make sure to check your homework and Canvas. Oh, also, just see your EID and make sure that it's on.
Yeah.
Because they're like, that's the yoga.
Alright. These were, do we tell your name?
Caleb Cardozo.
What's your last name?
Sorry.
Cool. Yeah. Do you not have rice?
Yes, I got the Empire State which is and I got the Yes, so I want to thank you again.
I was like, today. Well, I'm out.
You keep them.
Keep it.
Yeah.
Are you sure y'all don't want to reuse it?
No, we can buy them. That's for you to use. If you don't want it, why not?
Last time I saw was a Beagle.
Send an email to the class email. We'll get it sorted out. Do you think that this is
Well, it's the same subscription. You have to buy.
You shouldn't.
No, because I had it with you last
Right.
semester. That's why I was wondering why it wasn't.
Maybe, did you add late or something?
I mean, I hadn't checked this. Like,
No, I'm saying, did you add this class late? Like, when we sent them the roster, since the beginning, send an email to the class email, contact the class. Sure. Done? Thanks.
Oh no.
I tried to get out.
You did. No, I got quite a bit of you.
Just get sucked back to the podium and try to think about
Yeah.
what's going on.
I think we got more than enough footage. Yeah.
That's a fancy thing.
Yeah, it's really difficult to shoot. I can't zoom with it, so I have to, and I'm constant, and it's front heavy. I mean, this is a workout to have this thing.
Is this supposed to be like on some boom?
Yeah, it
moving
shoots in
around.
4K, which is the resolution you see in movie theaters. So this is a real paradigm shift that we got this. But it has limited battery life, and et cetera, et cetera. Yeah.
I don't want to shut this down. I'm waiting for Sparks.